I told you in the last video that epoxides are very reactive, that this little triangle right here, this equilateral triangle, is highly strained, highly unstable, so it makes it want to do something, get out of this configuration. So what I want to do in this video is to show you a reaction. So what we have right here, and we saw this in the last video, I've drawn a couple of more hydrogens, and I've actually drawn a little bit of the three-dimensional nature of the bonds right here, because it'll matter. This is cyclo, and remember, you can just pretend like this triangle here, if it was replaced with a double bond, this would be cyclohexene. This would be cyclohexene. But because instead of a double bond right here, we have these bonds to this oxygen, this is cyclohexene oxide. This is cyclohexene oxide. Let's think about what would happen if we had some cyclohexene oxide mixed in with water, and we have some type of maybe acid catalyst in there. So it allows some extra hydrogen protons to float around. So we have water, but since we actually put some acid catalyst there, and it could really be any acid catalyst, anything that would increase the hydrogen proton concentration, we're more likely to have some hydronium ions floating around. And we know what hydronium ions look like. They look like water with an extra proton, with an extra hydrogen on them. So hydronium ions look like this. This is water. Let me do it in a different color since I already used the blue for the cyclohexene oxide. So this is water right here. This is water right here. But what happens to get hydronium is the oxygen in the water takes a proton from someplace else, from some acid, the acid catalyst in this case, and so it would look like, and it would essentially give an electron to it. So if this electron gets given to some hydrogen proton, the ending result will look like this. You have a bond formed with another hydrogen, and now you have a positive charge. You have a positive charge on the oxygen because it gave away an electron. This is hydronium. We've seen it many times. Hydronium, and this is what results if you put an acid in water. It'll increase the hydronium concentration. You'll see more and more of this. So what's likely to happen if we have cyclohexene oxide in a water, with water as a solvent, but we also have a good amount of hydronium floating around. And the more acid we put in, the more hydronium we'll have. Well, a possible reaction well, let's see. This oxygen is just as likely, or it may want to get a hydrogen proton just as much as a hydronium. So if they bump into each other in the exact right way, this oxygen right here could give an electron to that hydrogen right there. And then the original, this orange hydronium, or this orange oxygen right here, can take its electron back. And if that happens, what do we end up with? Well, let's see. So if that happened, now we have, let me draw this original molecule. It will no longer be cyclohexene oxide exactly because it just got a hydrogen proton. It's an intermediary now. Let me try my best to draw it, though. All right, we have that. Then we have the oxygen popping out of the page. We have the oxygen popping out of the page. It had these two extra electron pairs, but now it gave one of its electrons to this proton. So now it gave one of its electrons to this hydrogen right here. And I call it a proton because a hydrogen without an electron is just a proton. It doesn't have another neutron inside of the nucleus. So you have the hydrogen over there. Now, since this oxygen gave away an electron, it now has a positive charge. Let me draw these two purple hydrogens that are behind the page. So that's one hydrogen there, one hydrogen there. Obviously, there's other hydrogens on these carbons, but if I were to draw it, it would take a while and it would make the whole diagram messy. But it's always assumed that a neutral carbon will have 4 bonds. And of course, this thing right here is now just water. This thing took its electron back. This thing took its electron back. I'll draw it here. This thing took its electron back, and now it's water. It could be this one, or maybe it could, but there's obviously tons of water around, so I could even draw other water molecules. It doesn't have to just be that one. Now, what is likely to happen? And this is kind of the fun part of this reaction, because it's actually something we've seen before. It's a reaction that we've seen many, many times already, but it's just not obvious when you see it in this form. When you look at this molecule right here, what's going on here? Well, I already told you that I have this highly, highly strained bond here. It's like this equilateral triangle. The bond angles are closer than they want to be. The electrons want to get away from each other. If you try to do this with a chemistry model, it would actually strain the plastic or the wood of the chemistry model to actually make it. On top of that, this oxygen with this extra hydrogen now, it is actually a good leaving group. And so now it's probably triggering some things in your brain about the type of reaction that might occur. And think about this carbon right here. Think about this carbon. Actually, these two carbons are the same, so I'll just pick on this one, the bottom one, for fun. Think about this carbon right here. It is bonded. It's a secondary carbon, so it's not, it would not be super great for an Sn2 reaction, but you can have an Sn2 reaction with a secondary carbon, especially when the leaving group wants to leave bad enough. So if one of these water molecules, and it didn't have to be this first one right here, if it just bumps into this carbon in the exact way, it can actually act as a nucleophile. Water isn't traditionally a very strong nucleophile, but it can be a nucleophile, especially if the leaving group is ready to leave, and this is a really strange bond. So what you could imagine is that, say, this water gives an electron. It loves this carbon nucleus right there. It gives it to that carbon. And since that carbon is getting an electron from this water over here, then it can release an electron back to this oxygen, making it neutral. So it can release this back to this oxygen right here. So what will we end up with then? Now something interesting has just happened. And this is typical of all Sn2 reactions. Remember, it's Sn2. We're substituting with a nucleophile. Water is a weak nucleophile, but in this case, it'll stick better than this thing that's all strained. And we call it Sn2 because both of the reactants are involved in the rate determining step. This is the rate determining step right here. So what do we end up with? What do we end up with? So let me just draw the hexane ring just like that. Now all of a sudden, this oxygen up here, what will it look like? Well, this bond gets broken. It takes back an electron. It takes back an electron. So you only have this bond to the oxygen, this top bond to the oxygen. That's the oxygen right there. It took this electron back. So now it has this electron and the electron that was bonded to the carbon. So it has a pair of electrons, and then it's bonded to that hydrogen that it took from the hydronium in the first step. And then it's bonded to this hydrogen over there. So it really is just an OH group now, bonded right that. It's popping out of the page. You still have this hydrogen that's going behind the page. You still have this hydrogen that's going behind the page. But since we had an Sn2 reaction, you can imagine this kind of came from the back and this let go from the front. So what will now happen is this hydrogen that was kind of behind the page now will pop forward because this guy went from even behind that hydrogen. So this hydrogen over here will now pop forward. So this hydrogen now has popped forward. I'll circle it just so you see it's the same hydrogen, but it's popped forward since this nucleophile attack happened from the back. And now he has attached down here. This water has attached. Well, it's not water anymore. So you had the oxygen, two hydrogens, and then it had two pairs, but now one of the pair turns into a bond because it gives this electron there. So these two guys are bonded. This electron is given to the carbon, and the bond is behind the page now. The bond is behind the page just like that. And then the final step is now this guy, since this guy gave an electron, he has a positive charge here. Just to make it nice and clean, you can imagine another water molecule comes and takes one of those hydrogens away from this guy. It's all these hydrogens are just getting passed around between these water molecules. So you can imagine this water molecule could take that hydrogen, this oxygen takes the electron back and then becomes neutral. And then our final product, we are now done, will look like this. Our final product, so we had cyclohexene oxide, and a reactive epoxide in water with some acid around. So it kind of catalyzed the leaving group and all that. We just saw that in this. But what does the resulting molecule look like? So popping out of the page up here, we have an OH That's this right here. I'm just simplifying a little bit. Going behind the page, we have a hydrogen right over there. And then popping out of the page, we have a hydrogen. So popping out of the page right here, we have a hydrogen. And then behind the page, we have another OH group. Behind the page, we have another OH group. So we've made a diol. And in particular, if we wanted to name this thing right here, we have our cyclohexane ring. That's our main ring. So let's call that. So we have cyclohexane. And then we have OH groups on there. We can just start numbering. We want to start numbering at where the groups are. So we call this the 1, 2, 3, 4, 5, 6 carbon. We have OH groups at the 1 and the 2 carbons. Then we have 2 of them, so it's a diol. So we call this 1, 2, 1, 2 diol, because we have 2 OH groups. Diol. That's the all is for alcohol. When you have these OH groups, we have 2 of them. And they are on opposite sides. This alcohol is, or this OH is popping out of the page. This OH is behind the page. So if we really wanted to be specific about even the stereochemistry here, we would call this trans. They're on opposite sides. One's in front, one's behind. So this is trans. This is trans cyclohexane 1,2 diol. So hopefully you enjoyed that. But the fun thing about this is, one, to see that epoxides are reactive, to just even see a new reaction. But the really fun thing to see is that these Sn2 reactions keep popping up. In fact, the ones we learned, Sn2, Sn1, E1, E2, these just keep over and over just popping up in chemistry in places that it wasn't obvious when you look at it, at the first glance, but then when you actually think about it, it's actually perfect for that type of reaction.